So, at Tesla, we don't make slow cars. We don't make this. So this thing has crazy power relative to a diesel truck. I mean, actually, especially if you're not towing anything, you could zip around like it looks crazy. Basically, it looks like an elephant moving like a cheetah. It doesn't look right, frankly. But this is not sluggish in the least. It's fast. It's fast to accelerate. It's fast to brake. It's really a step change improvement in what it's like to drive a semi-truck. Yeah, and we've got three times the power.
3 times the power than any diesel truck on the road right now. So you got all the work, all the power you need to get the job done. But the other reason that it's a beast is because it's also efficient. And you can go 500 miles on a single charge on one of these things. So it's the mix of those two that this is why this is a game changer. And what's awesome is both of those are enabled by our new 1,000-volt powertrain, which is the first vehicle that we're doing with that. And don't worry, there'll be some more vehicles coming with that. But this is going to be a game changer because of all the awesome innovations that have happened, behind the scenes and under the hood, so to speak.
Cool. Yeah. So we're obviously leveraging a ton of stuff that we've already done. So we've got well, it's now probably 51 billion miles driven. I don't know, it's more every day. So we're using our existing drive units, power electronics, infotainment, our super efficient heat pump, HVAC system, and state-of-the-art inverters. So we're able to leverage the existing powertrain and elements that are already made at volume in order to achieve extreme efficiency of cost and capability. So.
Yeah, and it also means we get to leverage all the reliability that the active car fleet is doing. So we're accumulating all these miles, getting a ton of demonstrated learnings into the field, and we're going to go and put all these trucks into the world and get a lot of learnings as well, but we're coming off of a great launching pad with everything that's done in the rest of our products already. And it's also enabled because Tesla's got this full vertical integration on the software and the hardware side. So the teams that are working together to put all that together into one package, this is a huge win, for all of our products, but particularly Semi.
Lots of hardcore testing. So, I mean, one of the things about a commercial truck is that the reliability has to be extremely high. So it's got to be running continuously, can't break down. It's got to handle every kind of weather. Uptime is super important for any kind of semi-truck. So we've tested durability in every kind of weather, every kind of environment. I mean, you could, yeah.
Yeah, I mean, we've driven Donner. We'll talk a little bit more about that in a moment, but we've been through hot, cold, snow, rain. We've been putting this thing through all its paces in the lab as well as in the real world. The simulation team has been doing an incredible job of being able to scale all of that, in the virtual side. And the other thing is that we're going to take these and we're going to put our money where our mouth is. And we're going to put these on into our own fleet, into our own supply chain. And we're going to use this to transport goods between our factories and our suppliers because we believe in it, not just from a mission perspective and a cost perspective, but because we want to close that feedback loop. We got to get that learning as fast as we can. We want it straight from the drivers. We want it straight from the service techs that are working on it. We're going to take all that data that's coming in and continue to refine the product and make it better, just like we do on the car side.
Yeah, exactly. So to be clear, like these semi-trucks are running 24/7 between Sparks, technically in Sparks, not Reno, but most people think of it as Reno Sparks, and Tahoe. And yeah, this is technically called the Tahoe Reno Industrial Complex, or TRIC. Now there's an interesting backstory about why it's called that.
Very.
Yeah. So, anyway, Tesla using the trucks continuously day and night between here and Fremont and back again is going to be a great test of the vehicle and will give us a great feedback loop for continuing to improve the product. So my click is sort of not working. There we go. All right. So yeah, we've got a tri-motor powertrain system. So we're using the carbon overwrap sleeve. So essentially, we're using the plaid Model S, Model X powertrain we're actually enabling the two of the drive units to actually disconnect so that they're not free spinning. So the efficiency is actually much greater in cruise.
Yeah, this is really unique. I mean, we're going with a tri-motor system. One of them is constantly engaged, so that's for maximum efficiency. You're getting on a highway, that's doing the bulk of the work, and it's operating at the peak efficiency point of the entire drivetrain. And then the other two units are for torque and acceleration. So when the driver needs it to get their job done, whether that's getting out of a loading dock or it's on the road, they need to pass somebody, you're tackling a grade, you have the torque and power to do it. And the cool thing is that these are clutched automatically, so no driver input needed, but it's also seamless. So the highway efficiency unit is cruising along doing its thing, and if the driver puts their foot to the floor, the torque unit spin up, clutch engages, and takes over, and it does all of that before we've maxed out the torque on the efficiency unit, so it's completely smooth. There's no turbo lag or jerkiness or anything like that. No driver input needed. It's smooth, both in terms of acceleration and deceleration for regen. It's really cool happening all behind the scenes.
Yeah, I mean, what I find actually really wild about this is that you can have a truck which is 82,000 pounds, and by the way, the reason we can actually do 82,000 pounds is that there's a 2,000 pound extra that's allowed by law for electric trucks. So you get a little bit of a advantage on the weight side. But you can basically pull 82,000 pounds at cruise using, and the only thing that's doing that is a tiny little motor on one axle.
Oh, that big, about football size maybe?
Yeah, you can carry it.
Yeah.
It's like a,
I mean, you can check it in your luggage. Good luck doing that with a diesel engine. And one of those is more powerful than a diesel. Yeah.
Yeah, just that one little guy is more powerful than a regular diesel engine on a semi-truck. But I find it amazing that this enormous thing can be pulled by something that you could carry in your hands. It's like, wow, that's power density.
Yep.
Yeah.
So yeah, and then in terms of, we're putting this to use in the real world. Yeah. So that truck's clocking it at 82. That's weighing 82,000 pounds. And when you see that pass shot again, you'll notice that speedometer is climbing. We're going 6% and accelerating up that grade. This is where it comes in.
Yeah, it's like driving a normal car, not like driving a truck. It's just that you're moving 82,000 pounds.
Yeah.
Yeah.
So any highway grade you come across, you can tackle at speed.
Yeah.
There's no compromise.
No slowdown.
Nope. And the other beauty is that you've got all this power going up, but you also have it going down. And what that means is you've got regenerative braking. So rather than using a Jake brake or engine braking like a diesel truck does, where you have to worry about hitting your shifts. If you miss a gear, you're onto your brakes and potentially in a runaway situation. You don't have to worry about any of that. There's no shifting, no nothing. And so the regen recaptures all that energy as you're going down these grades. But on top of it, it also is a safer system for not just the driver, but everybody on the road, because there's no gear to miss.
Yeah. I mean, it's worth reemphasizing that point. Because it's an electric drivetrain, when it goes downhill, or when you slow down, it recaptures the energy of motion or the energy of height. The potential and kinetic energy are largely recaptured, whereas for a diesel truck, that's not possible. You can't just create diesel. So you just end up heating brakes. And then your brakes overheat, and you can't use them, and then it's pretty dangerous because the brakes stop working.
Yeah, that's why you have runaway truck ramps.
Yeah.
Yeah. And it's funny because, if for any of you that have ever driven I-80 and driven Donner, there's a mandatory brake check stop for trucks down by Emigrant Gap. We've done this, and it's really funny because we'll go over the grade, we'll come down, and we just kind of pull to the side, and we're like, well, there's nothing to check, we've never used the things, and we just keep driving. Yeah.
Yeah. And we get to the bottom of the hill, we have cold brakes.
Yeah.
That's mind-blowing in the trucking world. So it's insane, basically. So it's really worth emphasizing that. That's a significant safety improvement for the truck driver and for other people on the road. We also have excellent traction control because the precision of an electric motor is vastly better than a diesel engine. It's sort of got I'm trying to think of the right analogy here, but it's got the precision of like a laser printer. It's not great. It's like really precise. That's what I'm saying. And the reaction is, so it's like you don't have to worry about, like traction control is awesome. It's got, it's automatically stopping the truck from jackknifing. It's doing all this safety stuff in the background that just isn't possible with regular diesel trucks. It's just, it's a step change in technology in so many ways.
Yeah, and the tight integration with the software team that we have here really makes that happen, because it means that we can take all that, the precision, and actually put it to use. You know, it's not some tie-in of some third-party powertrain. No, this is all in-house. As we do this really neat chassis control work at the brake level, the traction control level, we integrate with our total stability control system and make sure that the driver has a lot of confidence, but also has everything they need to stay on the road. It's going to be it's a really nice, neat integrated package overall in terms of software and control, and it's totally seamless to the driver, and it'll be a game changer in terms of safety.
Yeah.
So we talk power. You want to talk efficiency?
Yeah, absolutely. So, some people out there say it can't be done. I don't know who might say that, but I've heard rumors. So we just did it. Yeah. And we're going to post the whole video, unedited, on YouTube.
Yeah. And
no jump cuts.
Yeah. And this wasn't, some ultra clean, precise test track simulation or something where we, shut down a road. Nope, this is real world. This is over Grapevine. This is with traffic. This is true 500 miles. We were loaded just under 82K. We no special aero treatments.
Yeah.
Truck came off the line, shook it down, made it run. That's it.
Yeah, there was like no fast moves here.
Nope.
So to be clear, it's not like, what tricks did they pull? There were actually a whole bunch of tricks we could have pulled,
yeah,
and didn't. Like as Dan said, like no special aero treatment.
Oh, and by the way, we should mention there was no charging. Like we charged the truck.
Yeah,
we didn't stop the charge. Single driver.
One charge. Exactly.
Yeah.
Good point. So
minor detail.
Yeah, so it's not like 500 miles like with no load, with special aero and special everything. It's like fully loaded, going from the Bay Area. We actually have to like go a bit north to get to, actually add to get to 500 miles, because you can't, LA to the Bay Area is less than that.
Well, we went all the way to San Diego here. So we stretched out on the southern end. And I mean, do you want to see on the video? I mean, we have the proof.
Absolutely. So it's only 8 hours long, so.
Yeah, buckle in. Don't worry, we brought lots of snacks.
Yeah.
But yeah, standard trip. Down the 5, up Grapevine, through LA, traffic, construction. We got the bypass on the way station, but running full 80 or just under 82, full deliveries, nothing to hide.
Yeah, real world, it's, yeah.
He did take one restroom break for, there is a required mandatory 30-minute break within the first 8 hours of operation.
Okay.
Took a small restroom break, but that was it. Yep.
All right. Cool. So aerodynamic efficiency obviously matters a lot. You can see it's shaped like a bullet. It's really aerodynamic, and that helps a lot. As we get less than 2 kilowatt hours.
2 kilowatt hours a mile.
Yep. So.
And that's the name of the game. Is efficiency there. Yep.
Yep. So. Yeah. I mean, it's really efficient in every way, and.
I mean, the team's done a lot of awesome work. I mean, we went into the wind tunnel with this really cool model, rolling road, the whole 9 yards, and pulled in a lot of the learnings and all of our features from the car side that give us such great real-world efficiency there, and really want to make sure that the truck and the trailer have to work together. This is a combination. This is not just the truck. If you optimize one, you actually might disrupt the whole combination. And so we spent a lot of time, both virtually, but also in the wind tunnel to make this happen, and really some next level engineering to of everything they had to do there. And it means that we've got a really efficient truck.
Yeah. Welcome to Tesla AI Day 2022. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive. So should we bring out the bot?
Before we do that, we have one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes, mechanical mechanisms, no cables, nothing.
Yeah.
I want to do it with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
Go.
I think the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. Was on stage tonight. So the robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face. So we'll show you some videos now of the robot doing a bunch of other things.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot, and just walking around and dancing on stage. Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up.
We use the same process as we did for autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more.
What you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out.
Do it.
With the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. But Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000. The potential for Optimus is, I think, appreciated by very few people.
Hey!
As usual, Tesla demos are coming in hot.
So that robot that came out and did the little routine for you guys, we had that within 6 months. Built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue, our electrical system. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So we still are it's gonna do everything that a human brain does. Processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well.
So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. In the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side, angular contact ball bearing, and on the high-speed side, and on the low-speed side, a cross-roller bearing, and the gear train is a strain wave gear. There are 3 integrated sensors here and a bespoke permanent magnet machine. So our actuator is able to lift a half-ton, 9-foot concert grand piano.
Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback.
We're ported directly from autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. And this is a video of the motion control code running in the autopilot simulator showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months.
We wanted to manipulate objects while looking as natural as possible and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead.
I think the first thing within the next few weeks is to get Optimus at least at par with Bumblebee, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories and make this product a reality and change the entire economy. All of this was done in barely 6 or 8 months. Thank you very much.
Here you can see Sake, it's one of our other monkeys, typing on a keyboard. But now this is telepathic typing. So to be clear, this is he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, we can't actually spell, and so I don't want to oversell this thing. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. I think it's also important to show that Sake actually likes doing the demo and is not like strapped to the chair or anything. So So the monkeys actually enjoy doing the demos because they get the banana smoothie, and it's kind of a fun game. So I guess the point I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for the first 2 applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision.
We can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right.
So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. For implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. So here it is. That's our R1 robot with our patient Alpha, who is lying comfortably on the patient bed. This is what we call the targeting view. So what you're seeing is this is a picture of our brain proxy. And the pink represents the cortical surface that we want to insert our electrodes into, and the black represents the vasculatures that we want to avoid. So this is another view, real quick. On the left is the view of the insertion area, and on the right, what the robot's going to do is it's going to peel the array, the threads, one by one from its silicon backing, and insert it into the targets that we predetermined in the targeting view. So there you go. That's the first insertion. So we're going to see a couple more insertions. The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot.
Since I joined in 2017, we've also done a handful of iterations to optimize the thread insertions of the robot. One of the challenges that we've had to face has to do with the optomechanical packaging. So as you can see here, there's about 3 primary optical paths that are really valuable for us to have reliable thread insertions. One is the visible imaging of the needle inserting the thread. And then another is the laser interferometry system called OCT, optical coherence tomography, that gives us the precise position of the brain while it's moving in real time. And then also we have to provide lighting and illumination to see what's going on in the visible light camera. And doing all this where the needle is at the bottom of the craniectomy, especially when it's close to the skull wall, can be pretty difficult to fit everything and be able to see it. So the way that the team solved this is by putting all 3 of these optical paths into one optical stack using photon magic or polarization, whatever you want to call it. And that enables us to do vessel avoidance in real time. So as I mentioned, the brain is moving, and where we place targets in the beginning may not be where you want to insert at the moment the needle is going down there. So the robot can actually detect the vessels and then determine if we're going to insert onto a vessel or not, if it's safe to insert. And then that way we can avoid inserting onto major vessels.
So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the NeuroLink as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Okay, so here's a pig walking on a treadmill. And you may have seen something like this before in a previous NeuroLink presentation. But unlike before, this pig has more than one NeuroLink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. OK, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting. But if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial-temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. We have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider joining us here at NeuroLink. Thank you.